Okay. Let me, I guess, get started. I wanted to talk about in starting last class, we were talking about linear regression. I don't know if there's any questions that came up from that. I'd like to spend today talking a little bit more about finish up kind of how do you formulate good linear regression models before we get into the question of how do you actually, does a solver work that computes linear regression? And this is a good paradigm because I think a lot of modern machine learning methods use similar algorithms under the hood, and so I think it's good learning to deal with it. But I wanted to start off by talking about just a little bit more about good and bad things to formulate in your in formulating a problem where you're going to build a linear regression model. Now, one thing that you know, kind of if you think about it, should be clear, but maybe isn't obvious at first, is suppose, let's say, you have a target variable that you're trying to predict, and you've got a bunch of features. And these features, in your target variable, let's say you're trying to predict height or something like that, there is presumably some kind of a bell-shaped distribution, okay? And you want to make up range, if let's say the output is normally distributed, then when it comes to your features had also better be normally distributed. We talked about, if I want to make this distribution in some sense by adding constants times other distributions, the distributions ideally should have the same shape, okay? And this is why we talked about before about about if you have a power law shaped feature, okay, if your feature distribution was a power law, then it's not possible really to make some constant weight times the power law thing equal the normally distributed out target, something like height or something like that. So, one way to deal with it, as we said, was you should take the features and convert the features to something that's probably bell-shaped. That was by like hitting it with a log or something like that. Likewise, your target variable, what you're trying to predict, may very well be something that you want to convert before you do it. Okay, so that if you were trying to predict income, and you had, which is a bell-shaped thing, which has big numbers associated with it. If you, if you have normally distributed variables, you probably want to turn the target into something normally distributed. If you could predict a log of income, that is, that if you really needed to know, could be converted to income afterwards, and you'll probably do a better job of it if the feature distributions match the target distributions. Any questions? That I think should be obvious. One other thing that kind of, if you think about it, should be obvious, but tends to be a problem, is if you have a model where you're trying to predict something, a target from features, okay? More features is better than less features, we believe. But what happens if you have two features that are very, very highly correlated? Okay, suppose, let's say that we had two perfectly correlated features. Suppose that we were trying to predict some property of people's health, and we had their height measured in feet as one column, and their height measured in meters as another column. Now everybody knows, I guess, that you can convert between meters and feet by multiplying it by multiplying by a constant. a meter is something like 3.1 feet. So having these two features doesn't provide any more information in some sense than one of them. So you certainly don't need both of them in the model. But the thing that's maybe less clear is that having these two, in this case, perfectly correlated features can be damaging as well as this kind of not informative. One thing to note is that if you really do have a world where what you call it, the number of, one feature is a linear combination of the other, you're starting to get into a matrix that's no longer kind of a full rank, and you might have problems with when you're trying to solve a linear programming problem by a linear regression problem by using these kind of algebraic formula. You may find that suddenly your regression is going to crash because the inversion no longer works. So that's one problem with having two identically correlated features. But there's other problems, even beyond that. It should be clear that if you have, let's say that wealth is perfectly correlated. I want to predict wealth, and wealth can be well predicted from height. If I have the height in meters as a feature and the height in feet as a feature, I could build a good model that would be a constant times the height in meters to predict the wealth. I could build a good model to try to predict the height in feet, to predict wealth. It should also be clear that there's many, many models that are going to be equally good. Because I could have one coefficient here equal to 0 and all the weight on feet. I could have it all the weight on feet and nothing on meters. I could have half the weight on both. There are going to be a lot of equivalent models. So if you have a lot of models that are the same, essentially the same, it's hard to come up with a good explanation from looking at the coefficients of the model. So this is an argument that if ideally when we're building a model, we don't want highly correlated features. What is a way that we can take a data set and get rid of the highly correlated features? We could do it by computing the pairwise correlation between every feature and punt one if two features are very highly correlated above 0.9 or whatever you want to say, throw one of them out. The other idea is you take the matrix with correlated features and you try to compress them. This is what we were doing when we did SVD. We took a matrix which presumably had a bunch of correlated features. We tried to squeeze that out by compressing the matrix and lowering the dimensionality. This is the other way of dealing with highly correlated features. Any questions about this? Okay. Any other questions about formulating these linear regression models? Okay. Let me come back here. So what I'd like to now talk about is questions of how do you actually solve linear regression problems in practice. We saw that there is a classic formula for computing what linear regression, how to compute the optimal set of coefficients under the least squared criteria. That involve things like matrix multiplication and inversion. The good thing is it was simple, it was concise. The good thing is that, it's kind of amazing that that sort of formula can predict, can come up with the optimal coefficients. The bad thing about that formula is that, first of all, inversion is slow if you have a large data set. Okay, inversion is like an n cubed operation. For an n, to invert an n by n matrix is an n cubed operation. So that can be expensive if you have a large number of data points. It's also kind of brittle in that we're going to see that there's various other variations of regression that we might want to use. And these cannot always be expressed or cannot be easily expressed in these kind of these kind of linear algebra formulae. So this is going to be what motivates that we try to find other algorithms for solving regression. Okay, optimization kind of approaches. Okay, based on something called gradient descent search. Any questions? So what is the other way of thinking about what you call it, kind of linear regression? Let's say that we are trying to do linear regression. We were trying to find the best fitting line. So we do have the basic case of we have a y value we're trying to predict, a single x variable. There are dots in the plane, and we want to find what is the best line that fits that. That line is going to be defined by a slope and an intercept, okay? So if we're trying to find the best line to fit a bunch of points, one way to think about it is, we're just trying to find what are the values. Here I'm calling them W0 and W1 that happen to be the parameters for the intercept and the slope. What are the best parameters, W1 and W2? We can define a function that will measure how good any particular line is. And then finding the optimum line according to the error function will give us the regression line that we want. So what is this equation here? Suppose, let's say that we have a regression line, or to be precise, a candidate regression line. W0 is going to be an intercept of a line. W1 is going to be the slope of a line. How good is that line at predicting, at modeling the points? Well, my claim is it's going to be the sum over all the example points of the difference between the y value of the point and the predicted value of y that we get by using our model W0 plus W1 times x. This is y minus f of xi is going to be the residual. The residual squared is going to be the sum of squares. Is going to be the square of the residual. The sum over all points is the sum of the squared error. Okay? And so this formula gives you a measure of how good W1 and W2 are at fitting the points. It is exactly computing the mean squared error, the squared error. And in fact, since we happen to divide it by 1 over n, forget the 2 for now, okay? We happen to be getting something like the mean squared error, okay? Any questions? Okay? So what's good? We have a formula for judging how good a given regression line is. We have our regression line as being thought of as a point in two-dimensional space, okay, which has an associated error associated with it. One way to do this now is to try to find what are the set of parameters, the set of W1 and W2, that minimizes this error function. Here was our error function. Okay. Here is a space, if you wish. Okay, a way that I would think about it. Here we have a space where this is W1. This dimension is, sorry about that, W1. This dimension is W0. For every XY point in intercept slope space, we'll define a particular line. For each one of these points, we could think the error value would represent a third dimension. You can now imagine our linear space of linear regression models is going to be for three-dimensional points. The first two are the parameters of the line, and the third is going to be the error. What do we want to do? Our goal for finding the best, regression model means trying to find the x and the y point such that the error value is minimized. Okay? If we find that point in parameter space, that will give us the optimal line. Okay? Any questions about this formulation? Okay, I like this formulation. I think this is a lot better than the linear algebra thing because I kind of understand it now. Okay, there is a direct error function that I described. I understood the error function. Okay, I know that I want the point, the set of parameters, the slope and intercept, that minimizes the error function. This formulation now reduces linear regression to finding the minimum point in this error surface. Okay? And by some form of magic, luck, I'll call it luck, okay? It turns out that the error function is convex. What does convex mean? Convex means that there is a single local minimum, okay? A single lowest point. This is a slice through the, the error surface, okay? Here we're assuming that W0 is 0, okay? And when you look at this thing, if you look at any slice of this thing, the error function, there is a value of the coefficient W1 such that it minimizes the error, okay? In general, when we had the two variable things, we had a bowl. It had a kind of a downward shape. And there was only one, because this function was convex, the definition of convex meant that it had only one local minima, and that local minima therefore had to be a global minima. So if we can find the lowest point on this error surface, we will have found the optimal regression line. Any questions about that? Okay. So how do we find what is the lowest point on the on the surface? We can, because the space that has only one, the space is convex, it only has one minima. Okay? If the space is convex, the surface here is kind of like a bowl. Okay? And finding the lowest point is, in principle, easy. You just have to keep going down. Again, if this was a bowl, how would a marble find the optimal way to go? Again, I kind of picture this is a bowl, it's curving down. If I put a little marble here, a marble is a sort of a sphere, it will, kind of by the force of gravity, roll down. It might then overshoot because it has too much momentum. But then eventually it's going to go down and boop, boop, boop. And it would eventually settle at this lowest point. So long as we are at a point, for every point on the error surface, we know which direction points down, then we will eventually get there. If we took our marble and instead of rolling it straight down, we rolled it, we gave it a little kick in one direction, we might spin and circle around for a while. But again, we would eventually, okay, as it lost energy, end up at the bottom of the bowl. This is what we want to do, okay? Not with physical bowls, but by simulating the bowl, okay? Basically, given a point where we are on the surface space, if we can find a direction that goes down, we will walk in that direction. Ideally, we will find the fastest direction down. And the fastest direction down is defined by kind of the tangent line or surface or the slope, okay, at the current point. Any questions? So what is the idea here? If you are at a particular point x, y, how can you find the, which direction is down? In 2 dimensions, if you have a convex function in 2 dimensions, there's only 2 directions you can go. You can go up or you can go down. How do you know which one of these is down? One way you could tell, okay, could have been, again, when I took calculus, the simplest thing to do would be to estimate the slope by taking my point, add some, delta to x. This was a point xy. Add x so that a delta x to x. So I move to a nearby place. I see what the y is at this nearby place. Now I've got 2 points, okay, that are on the surface. If I took the, if I took a line and fitted it through those 2 points, the slope of that line will tell me whether this direction, if the slope is downward, this going in that direction was a good idea, okay? If the slope was upward, okay, it was a bad idea. Basically, by doing this, I could figure out the slope of the line, and that will tell me which direction is down, and I can walk in it going down. Any questions? So finding the tangent line numerically, this is something that, by just taking, a point, in a delta neighborhood around it, that would be one way to figure out what's up and down. But the other is to use, the full weight of calculus and, try to use derivatives to count the way, to identify the way down. Symbolically, the partial derivative of a function relative to a variable would describe what is the, what is the slope or the gradient, okay, in that variable. Which way should I change that variable to go up or down, okay? And, when you took calculus, you learned how to take derivatives. If you had a multivariate function, you learned how to take partial derivatives, okay? Derivatives with respect to a particular variable. what is the partial derivative of this polynomial with respect to variable w? Well, you know, 1/2 n is basically just a constant with respect to w. You have w plus a constant term raised to the square, okay? The derivative with respect to w, you would lower the exponent, the 2 goes down, and the 1/2 and the 2 cancel, and what's left is the partial derivative with respect to w. Yeah. N should be a variable, but it's not the variable that we are taking the partial derivative of.
Yeah, but that is 1/2n, right? Of what n? I mean, n is.
Okay, I see. So, okay, wait a second. So you're telling me.
I think this mistake is because of the way that you write this formula in Mathematica.
Right. I did write this in Mathematica. Right. Okay, so what you're telling me is that this is really, should be 1/2 n and not 1/2n. This is supposed to be 1/2 n. So this is really n over 2. And when it's n over 2, then when I took the derivative, the 2 came down. And so right, it's not 1/2n. Okay, we're agreeing. On the second one, if we took the derivative relative to a different partial derivative relative to a different variable, here s, the derivative was, again, we dropped by 2. We also had the term, the derivative, it was, drop the exponent, take the derivative of what's inside the polynomial. The derivative with respect to s would be, we lower the degree of s, what's left is x, that's where the x comes down. Bottom line is, there are, derivatives, as we remember, had to do with telling you what the slope was, the rate of change at a point. Partial derivatives tell you what the rate of change is at every dimension of that point, okay? And this, by computing partial derivatives symbolically, this gives you the way of computing which direction is down from a particular point. Any questions? So what is the idea of using gradient descent search for solving regression models? Okay. Again, what do we know? We have in a linear regression model we want to fit. Here it was a line with 2 parameters, meaning it was in one variable and an intercept. We had an error function that we sought to minimize. Okay. What you call it? Which was basically the predicted value minus the actual target value summed up over each point and square the error. Okay? We wanted to minimize that sum of squared errors, or equivalently, the average sum of square errors. Okay? How did we do it? The gradient descent algorithm said, start with an arbitrary value of these parameters, sigma 0 and sigma 1. Okay? Then update until you repeatedly update until you get to a minimum, until it doesn't change. How are we going to update it? For each parameter theta j, either 1 or 0, we're going to take the new value is the old value, okay, minus the partial derivative at this point, which is what tells you whether it's going up, how to make it go down, how to make the target value go down. This is the partial derivative of the error function, okay, with respect to the jth variable. This will tell us what direction do we want to change this parameter. And we're going to multiply that by some value alpha, which is once we know the direction that we want to go in, how big a step do we want to take in that direction? Okay, that's what this algorithm is telling us. Okay, we are going to we have a current value of our we have a current value of our parameter. We have a direction to move, where if we move in that direction, we will infinitesimally, we will lower our error value, okay? And we're going to take a step of length alpha, okay, in that direction, okay? It's in an attempt to lower what we're doing here. Any questions? So this is what the gradient descent search algorithm is, okay? It is going to keep walking until it gets to the point where the error function doesn't change. If the error function doesn't change, then the derivatives are going to go to 0, and then 0 times alpha is going to be 0, and we're going to stay where we are, meaning we have converged. Any questions? Any questions? Yes.
Alpha should be constant during the whole process, then we can change it.
Okay, in this, as written here, alpha is a constant through the whole process. But are you free to change it? You're certainly free to change it as you go around. Okay, what is going to be, and that's an important question. What is the impact of changing this alpha? Okay, actually, I've got. Let me talk about that now. That alpha is going to govern something that we call the learning rate. Okay, what is that? Alpha is sometimes parameter is sometimes called the learning rate. It's the step size. Given that you're at a partial solution, once you have figured out what's going down, alpha is going to govern how big a step you take. Okay? It should be clear that if you're far from the goal, and if you're far from the goal, and you're thinking alpha is small, you're going to take little steps towards the goal each time. And if alpha is too small, it's going to take many, many, many steps to get towards the goal. It should also be clear that if alpha is too large, and let's say you're relatively close to the goal compared to alpha, taking a step in a particular direction might well overshoot the goal. And you could imagine going from one side to another, okay, not really making progress towards getting to the goal. If alpha is too big, okay, if I know that for me to get from here to my home, I have to go in that direction. If I took a step of 2,000 miles, I'd end up in the ocean, okay? And I'm not really getting closer to it. So picking what the size of the step does make a difference. If I use a constant, like I was asked before, setting what the right constant is unclear, and setting the and whether it stays a constant. It should be clear that maybe something that made big jumps was good when I was far from the goal, but bad when I'm close. Okay? It should be clear that I want the power to change my learning rate. Okay? And so in practice, although in the, in the gradient descent search solution I had before, I had alpha, my learning rate is a constant. In fact, there is no good reason why alpha should be a constant. Okay? What I probably should do is make a good guess about what my alpha is at the beginning. Okay? And then monitor how the loss function is changing, okay, over time. There's this error, this this error that was left, the sum of squared difference between my target, my current model, and the actual point. If J is not decreasing fast enough, then I probably would want to multiply alpha by something, like let's say 3. Okay, and that will then make faster progress towards the goal. If, on the other hand, my, the error increases instead of decreasing after a step, that's a sign that I took too big a step. Maybe I should decrease my alpha by multiplying it by 1/3. Okay? So when you're doing this kind of machine learning, there are various library functions or algorithms people use to try to set the learning rate. Something called the atom optimizer that tries to set what the learning rate would be based on how fast you're making it towards a goal. Okay, and so you're right. So when we look at my simple my simple model here, there's no really good reason why the learning rate needs to be a constant. Okay, I can and probably should change it when necessary. Any questions about that? Okay. So what else is there? Now, the good news is that if my loss function is convex, then taking a walk in a always going down is going to give me an optimum. How do I know whether my loss function is convex? And this is a complicated question. But again, you sort of knew when you were taking calculus. Okay, in calculus, they were talked about issues of when did functions have single minima or not. Okay, when you took calculus in a low number of in one variable. Okay, you knew that whenever the first derivative was 0, you got a maximum or a minimum. There were some things that happened when you took the second derivative. Okay? The claim is that if you take a course in convex functions, you will be able to analyze the derivatives of a function and be able to tell whether it's convex or not. Okay? This is beyond the scope of what I'm trying to teach here. But in principle, certain functions are convex, certain functions are not. When you were taking calculus, that you were in the neighborhood of such things, okay? But the analysis of the derivatives are what will ultimately tell you whether something's convex or not. Any questions? Yeah.
It's not true. Whenever the first derivative is 0, you get an absolute minimum. For example, if f of x equals x cubed.
Okay. Which function are you talking about?
F of x equals x cubed.
6 cubed? X cubed. Yeah. Okay. Now, the claim is that, okay, when you have that function, well, let's just think about it. What x cubed, what is the derivative? What is x cubed? For a positive value, x cubed is going to be, convex on that side. For a negative value, what's going to happen here? It goes down, right? Now, here is one where, this function over the whole range is not convex, okay? It does not have a single minima. And the claim would be that, again, this is sometimes, I think, called a saddle point, if I remember correct. It's a change in derivative, okay? This is why this is more complicated than just what we did. You guys knew about finding maxima and minima when you took calculus. It was also more complicated. There were things that called saddle points and other things going on. Bottom line is certain functions are convex, certain functions are not. People who know what they are doing, if they analyze the derivatives and the second derivatives can kind of make a sense of this, okay? If you know your function is convex, then you can know that when you do a gradient descent search, you will find the optimum, okay? If not, if your function is not convex, what happens when you do a gradient descent search? Okay, here we have a function that is not very convex. It is not convex at all. It's got multiple maxima, it's got multiple minima. What happens if I start from a particular point, okay, and start walking downward, okay? If I keep walking downward always, okay, like I was doing with gradient descent search, I will eventually end in the bottom of a local minima. Is that local minima, necessarily the best globally? Here we've got many different local minima, okay? Does this mean I can't use gradient descent search to try to come up with improve my model? Let's say this was the error surface of my model, okay? And I'm trying to find the parameters that optimize the error. Suppose it wasn't a convex function. If I keep walking downward so long as I can, I am going to eventually end in a local minima. Okay? Is this good? Okay. So I guess I'd say it's not good, but it's not terrible. Okay? What do I know about this local minima? It's a better model than it was at the original point. And what could I do now? I could conceivably start it again someplace and hope that when I find the local minima from there, okay, that this will be better than the one that I had before. So could I use gradient descent search to try to optimize non-convex error functions? The answer is yes. I lose the guarantee that, that I'm going to end up at an optimal solution, okay? If I knew it was convex, I would only do one such walk, okay? If it's not convex, maybe I'm going to try sampling it at different points and see what happens, okay? Am I likely to find the absolute global optima for a non-convex function? No. Am I likely to find some parameters that are probably pretty decent? The answer is, depending upon the shape of the error surface and how long I'm willing to look, probably yes. So the convex guarantee is good for proving that I'm correct. It's not necessary to apply a gradient descent approach to try to optimize the parameters. Okay? Any questions about that? Okay? But it is if you know the function is that you want to optimize is convex, then you can rest much more easily than if you don't. Any questions? Okay. And again, we discussed this idea of the learning rate, the step size, and that's a parameter that you have to play with, at least to guess what the right one is, or to adjust it in order to come up with a good optimization. Any questions? Now, what is the running time? Actually, here's a good question. Let's go back to this model and say, what is the running time of this algorithm? Okay? Let's imagine this. We've got a world where, let me put it on, just clear this thing out. Here we've got a world where we've got, let's say, in this case, we've got, what am I going to say? We've got n parameters. Here n equals 2, okay? We've got m points. How many times are we going to repeat this, this loop, till it converges? Depends on something unforbid. Let's just say it repeats a total of r times, okay? Let's say that we're willing to run a total of r of these steps, and then we're going to give up, okay? What is the running time of this algorithm as a function of r, n, and m? Okay? If we look at this algorithm, what is that running time going to be? At each point here, what am I going to do? I'm going to take my n parameters, okay, and I'm going to update it. So this is going to be r times n, which is the number of parameters, times what? I claim the time here is the cost of computing the derivative. Okay? Right? I'm plugging in for each one of these times. Let's say I had computed the derivative symbolically. Okay, here was my derivative. I took the derivative of this. What was the derivative? I presumably dropped the exponent down. I may or may not have a an x or something like that. This is the cost of computing the partial derivative. Once the partial derivative is evaluated symbolically, what is the cost of computing that partial derivative? If we think about it, how many terms are there going to be in the partial derivative here? Okay? In the error function, how much does it cost to compute the error function itself? What? It's going to be something like m times n. Does everybody see that? To compute what j is, okay, it's going to be the sum of m terms. For each one of these m terms, I'm going to have to compute my regression model. I'm going to have to evaluate my regression model on the input vector of that term. In this case, there were 2 parameters. My claim is that it will cost something like m times n to evaluate the derivative at any point. Okay? Does everybody see that the function, again, I don't have on my slide what the function is, okay? What the derivative is. But the error function itself is what? It is a polynomial, but it is in n terms, okay? Each of which has m parameters involved. It will take order m time, m meaning the number of dimensions, to evaluate this on each one of the n input vectors. So for a given value of alpha of omega, theta 0 and theta 1, okay, whatever that theta vector of parameters is, okay, computing what this error function is takes time proportional to the data size of the data set. How many points times how many dimensions? The point being, the cost of computing the derivative is an expensive thing. Okay? Any questions about that? Yeah.
Can you explain why should we take into consideration all of the endpoints for using the
Should I or shouldn't I? Okay. Clearly, right now, I am. That's what I want to say. We can argue whether I should or should not take into consideration all the training points. Okay. But it does clear, see, that this innocent looking, simple looking algorithm, one Achilles heel of it is as it is formulated now. J prime, does everybody agree that the derivative of this thing is also going to include a summation of all the points, and also going to be for each point going to evaluate the regression model, so it's going to involve the same number of dimensions. Okay? As written now, the cost of computing the derivative is basically the size of the entire training set. And this tells me that this algorithm, gradient descent search, is going to be the number of iterations times basically the size of the training set times the dimension again. Okay? So in order to solve a large problem, we need to find faster ways to compute what that derivative is. Okay? And that's what's going to kind of give us the idea of something called stochastic gradient descent, which is the real algorithm that people use for training these kind of machine learning models. What is the idea? If evaluating the partial derivative at any point, okay, takes time linear in the amount of examples, if you have a big training set, this is going to be expensive, okay? A heuristic that you can use is take only a few of the examples, perhaps picked randomly, okay, and estimate what the partial derivatives are just using the small set of examples, okay? The good thing is, if instead of using 1,000,000 examples to estimate the partial derivative, to compute the partial derivative, I estimate it with 10 examples. What's the good thing? The good thing is my partial derivative calculation is much faster than the old one. What's the bad thing about that? Suppose I use only 10 training examples out of my 1,000,000 to estimate the partial derivative. The precision, it's not clear that, what improved these, if I get very unlucky, what improved these 10 examples actually worked away. These 10 examples might have been weird relative to the original data set. It might even move me away. The estimate of the derivative might not be reflective of the full data set. So the good thing is with stochastic gradient descent, if I estimate the derivative on a few examples, each iteration will be much faster. I can run more iterations, okay, in a given amount of time. The bad news is my estimate for the direction of which direction is down is not going to be as good, okay, and so there is a trade-off. And in trying to do one of these optimizations, one other new parameter we have, like the learning rate, is something called the batch size. How many, how many examples should we use to estimate the partial derivative? With one example, it would be very fast. You would compute the derivative in constant time. Bad thing is, you don't know that it's necessarily right. There is some kind of a goal where you would like to use a big enough batch size that it is informative, but a small enough batch size that it is quick. Okay? And this is kind of what part of the art of combinatorial optimization. Okay? That, But if you do it right, you will have a fast iteration, and each and your estimate for the which direction to move in is likely to be pretty decent. Any questions? So this is what is stochastic gradient descent, and it is the I will say the primary algorithm used in training many types of machine learning models, including deep learning and things like that. Any questions about that? Okay. Okay, so this is how, in practice, big linear regression models are solved. There is one other question that comes up in designing, in linear regression models, which is that typically we're going to try to predict our value y as a function of m variables. When we were building our feature matrix, we probably tried to make our matrix as big as possible because we want as many features as we can. Now, it's often the case that not all the features really, really are important to making a prediction. Okay, we talked about Occam's razor. Occam's razor said that the simplest explanation is best. You could imagine a world where when you're training a regression model, okay, the best model on all, if you have a training world where you have a finite number of training examples and you've got a large number of features, the absolute best model is probably going to use all of the features to try to absolutely minimize the error on the observed training set. Now, much of that observed error, okay, is going to be weirdnesses of the training examples. It would be good if we could to have our linear regression not only optimize the the coefficients of the variable so as to fit the data well. We would also like it to identify which variables really don't contribute to the to the model, okay, in an important way. Occam's razor says that a model with a small number of variables that does a very good job of coming up with an answer is probably better than one that has a large number of variables and does slightly lower in the error metric. Okay? What we would like to be able to do is to have the regression machinery augmented so it favors simple models. It favors well-fitting models, but it also favors simple models. And doing that, that is the idea of regularization. Any questions? What is regularization? Regularization is the idea that we're going to want to add a term to our optimization function. Okay? So that when we, our optimization function or criteria, okay, we want our error function to simultaneously try to minimize the error, maximize the quality of the fit, while also keeping the coefficients of the model small. Okay? We would like it to be a good model if you have a lot of potential variables. The model that might be most interesting would be one that throws out a lot of variables, meaning sets their coefficient to 0, okay? And also doesn't have very, very large coefficients. Again, I know you guys fit some regression models. Sometimes you will have, when you solve a regression thing, you could imagine a world where, um, when you try to find the optimal regression coefficient, okay? Sometimes, okay, let me take a look at it. Sometimes you have a world where, what you call it? You have a model. Let's say we have a model of the form y equals, let's say, c1 times x1 plus c2 times x2. Okay? Let's say that x1 and x2 are about the same order of magnitude. Okay? Let's say that, they're both, let's say, even z-score things. Something that sometimes happens is you could imagine something, let's say y was equal to a value that's typically also a z-score. So it's a value between, let's say, -3 and 3. Sometimes you could imagine a world where there would be a model that would take this thing times 1,000,000 and multiply this variable times -1,000,000, 0.2. Okay? These are kind of the fitted coefficients. Occasionally, in trying to find the absolute model that is best going to do things, if you leave the what you call it, the regression to its own devices, it will try to fit it by having a very, very large coefficient times a variable, offset by taking another coefficient, okay, that was, and subtracting it off, basically to make this thing lower. An almost as good model, if you have something like y equals 1,000,000 x minus 1,000,000 y, that's almost going to be the same model as y equals, x minus x1 minus x2. Okay? So when you fit these models, sometimes if you don't take efforts to lower the coefficient sizes, there'll be many equivalent sets of coefficients that might realize the same, about the same error. Typically, if we have small coefficients, okay, it's easier to interpret what the model is, okay? And so we'd like to add a term to our optimization thing with the desire of keeping our coefficients small. This is the idea of regularization. What might we do? If we took our error function before, this was the error function over here, corresponding to the sum of squared differences between the prediction and the other thing. This here is a separate term where we're going to add to the error cost a constant lambda times the sum of the squares of the coefficients themselves. You see what we're doing here? If the coefficient vector was this theta vector, this is going to say sum up the squares of the coefficients, and we're going to have lambda times that added to our error objective. If we now try to find what are the parameters that minimize this error function, what is the way we should do it? Well, in the parameters will try to minimize the the sum of squared error. while also trying to keep the coefficients small. Something like the case of 1,000,000x minus 1,000,000y is going to involve very, very large coefficients, which when you square them become very, very large. Okay? The model that is going to be the most desirable one, okay, is going to be, what you call it, the one which has small coefficients while still doing a pretty good job of fitting the data, okay? And by changing our error criteria, we will now fit a model that won't do quite as good a job of fitting the points, but will fit the points quite well, ideally, while having small parameters. And that's actually a probably better model to use. Any questions? Okay. So this is the idea of regularization. How should we set, any questions about that? How should we set this value of lambda? Lambda is a coefficient here that's going to do what? It's going to trade off, determine what is the trade-off in our desired model between things that fit very, very well and things that use small coefficients in the model. Okay? So what is the best choice of lambda here? That's hard for me to tell you. But it is, I can tell you that if you play with different values of lambda, okay, as lambda increases, it's going to focus more and more on making the coefficient small and less on slavishly fitting the minimizing sum of squares. Okay? And ideally, you will find that for a modest value of lambda, you will get almost as much sum of square accuracy while having much smaller coefficients than if you didn't regularize. Any questions? Did any of you in the course of when you were using linear regression for the homeworks, did anybody do regularization? Okay, yeah. Did you have any experiences? I mean, did you try different values of the regularization thing, or you just went to the library and said, just use the library, okay? And ideally, what would a library like that do? It might have, what you call it, it might fix, again, God knows what's in the library. It might fix a single value here. It might try a couple of different values of lambda and see what the trade-off is. How much better does the model get to try to take something like that? There's someone on the web who also used regularization, on the TV, who's also used regularization. Did anybody try doing it both with regularization and without? Okay. And did you look at the models with and without regularization to see what actually happened? Okay. He's saying he specified values for them. Did you see improvements or differences when you tried different ones? If Hugo, if you want to talk. Okay, you saw values. Okay. How big a difference did you get? Okay. Typically, what I think you will find is that a small amount of regularization will have a small effect on how well it fits, but a large value difference in how what the parameters look like. Okay, and the models, when you use regularization, are often much more robust than the original than if you don't use regularization. Any question? Again, when you add regularization, what you're going to end up doing, the training error on your points is going to be worse The hope is that the model that you get is going to be better at fitting the things that you're going to use in testing that you're not seeing. Okay? Because if you don't have the regularization, it's going to kind of overfit the training points. That's kind of why we have this thing here. Any questions? So, okay, so how should we think about these coefficients? Again, in an ideal world where, let's say, if you have a regression model where all the variables were z-scores, okay? If the variables were z-scores, okay, then every variable has a mean of 0, okay? If all your variables are kind of, comparable in magnitude and scale, one thing that's good about that is that we can interpret the model by what the size of the coefficients are. Okay, if the variables are all roughly of the same scale and range and magnitude, okay, having a positive coefficient means that variable presumably correlates with the target. Okay, a negative coefficient presumably means that it is inversely associated with the target. A coefficient around 0 means that variable is not very important. And when you fit the regression models, it's often the case that you'll see a lot of coefficients really around 0. These are things that probably are, that if you have a correlation coefficient, no, if you have the coefficient in the regression model, okay, if that coefficient is close to 0, that means that that variable is not having much effect on the prediction of the variable. One way to simplify the model might be to look at the coefficients, and any coefficient that's close to 0, maybe explicitly make it 0. This is one way to reduce the number of features in a model. Okay? The other is to use a idea, instead of doing that on kind of an ad hoc basis, would be to use a principled form of regularization. We talked before about minimizing the sum of the squares of the coefficients. Okay? This is something that is going to make the coefficients small. Okay, that's called ridge regression. Another idea is, instead of minimizing the sum of the square of the coefficients, like I did here, you could imagine minimizing the absolute value of a coefficient. Okay? If we do that, that's something called lasso regularization. The lasso regularization has some theoretical properties that causes it to not only make the value small, but if it can drive it to 0, it tends to drive it to 0 more. Driving a coefficient in a linear model to 0 is equivalent to removing the variable from the model. Okay? And so lasso regularization is a good way to reduce the number of variables in your model, okay, without really affecting the performance. Any questions? Okay. Again, how do you set the right value of lambda? I guess I talked about this. Okay. Oh, actually, the lambda in the regularization. If you have a big lambda, it's going to want to make all the coefficients small. If you have a small lambda, it's going to want to make the training error small. Okay. And again, you have to decide from your own experience, okay, whether whether you're more happy with overfitting, which is what happens when you have a small lambda, or underfitting, which is what happens when you have a large lambda. Ideally, there is a right one, that gives you better performance on the test set. Okay? Any questions? Now, when you think about, again, Occam's razor said that we wanted to find the simplest explanation that fits the model. Again, if we have the more parameters we have, the more we will minimize our training error. Okay, the better we will be able to, in principle, fit the training set. Occam says that a variable model with a few parameters is more robust. Okay, so how do you figure out what the best model is? The best model is a function of a model with fewer variables, fewer parameters is better. A model that has a better training error is better. Okay, and they kind of work against each other. Bottom line is that there are some formal criteria, some way of scoring, okay, what the trade-off is of the number of parameters and the amount of fit, okay, that sometimes these training systems will use, okay. Perhaps the version of regression that you had where you did regularization and you didn't specify it. Maybe it's trying a bunch of different, okay, values of that lambda, okay, and then scoring the models based on how well do they fit and what the number of non-zero parameters is, okay. Bottom line is that there is a trade-off. Bottom line is that generally adding regularization is a good idea, okay. Adding regularization was an easy thing to do in this optimization framework for models. Okay, it was just adding an error term. When we talked about linear regression in the beginning, okay, when we talk about linear regression in the linear algebra approach, okay, we had a nice normal form, okay, for computing what the coefficients are, okay. It turns out that you can generalize the linear, the linear algebra formulation of regression, so that it becomes, that it incorporates regularization. Okay, but the formula gets more complicated. Someone had to be smarter about doing it. The good thing about the gradient descent approach is that we can directly set our error function to be what we want, to incorporate what things we think are important, okay, and just set the optimizer under those conditions. Okay, any questions about linear regression or optimization? Yes.
L is based on training data, or
L is presumably based on the training data. Okay.
then only the first element of the matrix is 0.
Okay, according to this, why is this 0? This is, I believe, these are the coefficients. Now, this is the intercept. If you think about, let's say, what are the coefficients in setting a line? Remember that when you have a coefficient of the form, a line y equals omega 0 plus omega 1 times x plus omega 2 times x1, x2. Notice that most of the parameters are representing coefficients of a variable. The first coefficient, okay, is a coefficient of basically times 1. It's a constant term. And so the asymmetry, why is there a 0 here in this formulation? That 0 is not on variable x3. That 0 is on the intercept. Okay, and that's how it works out, that this is a different kind of thing than the other. So do I believe that the coefficients from 2 through m are different than the coefficient for 0, I can believe that because one is for an intercept and the other is for a weight. Okay? Any question? You're never, I guess another way to think about it is you're never trying to drive out the intercept. If you think about why should that thing be 0? Typically, if we're trying to minimize something, you're never going to be, you're generally not going to try to drive out you don't want to drive the intercept value out from the model. You want to drive the variables out of the model because the variables are where the complexity is. And that's presumably what is reflected by that matrix. Any questions? Okay, if not, thanks for your attention. And next class, we're going to look at using these, the kind of generalizing this idea of linear regression to problems of classification. Okay, we start talking about logistic regression. Okay, thanks for your attention. I will talk to you guys next class.